the engineer lectures. We started the term with a wonderful exhibition and lecture by the Swiss engineer Jörg Konzett, and have had a whole series of very interesting presentations, and it's my pleasure to welcome James Carpenter and Tim Macfarlane to be the last presenters in this series. I would also like to thank James Carpenter for really putting together a fantastic, wonderful exhibition that all of you hopefully have had a chance to see. If you haven't, I would certainly recommend that you spend some time really carefully looking at the work. I would like to thank Marek Walczek, Luke Lowings, Richard Kress, and Lee Morrow from Jamie's office, and Richard Woodgate, and Andrew McKenzie, Nicola Hood from the AA, who also have made the exhibition possible. It is, in a sense, I think the exhibition that's on at the moment, a very important contribution that crosses the boundaries between architecture, engineering, and art. But in a sense, even more importantly, for me, I think what Jamie has done is to also cross the boundaries between architecture, design, and issues of fabrication. Because for a long time, one can say that architects have been in many ways disengaged and disempowered in relation to conditions of fabrication. And one has to really go back to people like Jean Prouvé to find a different kind of practice which didn't go directly from design to fabrication, but the very constituency of design itself had a very deep understanding of the conditions of fabrication. You could say that someone like Prouvé was incredibly knowledgeable about the kind of thickness of line that he was drawing when he was dealing with his wall sections or with his windows. And I think one can sense something of that quality in the work of James Carpenter, where it's not really, in a sense, a representational architecture, but it's one where it is more to do with the specialities, the qualities and conditions that derive from the work, especially in the case of glass, these issues of transmission, reflection, refraction that have been referred to. The first lecture, however, will be given by Tim Macfarlane, and it's really wonderful to have Tim back. Tim was the head of the Diploma Technical Studies here until he escaped to go to the States, and it's good that he's here. He has been really instrumental, I think, in the UK for bringing to our attention the wonderful things that are possible in terms of the use of structural glass, but generally the use of glass in construction in ways that many architects have yet to utilize. And we were fortunate to publish one of the projects from the firm Dewhurst Macfarlane for the canopy for the Tokyo Forum. That was one of the key projects. And recently also the firm has completed the glass cube reading room for the Arab Urban Development Institute in Riyadh, as well as many other projects that Tim has been working on in New York. Would you please join me in welcoming Tim Macfarlane?
Thank you, Moisen. It's a lovely welcome back, and it's a lovely feeling to be back. Obviously, I'm slightly nervous, so it's not a fantastic feeling, but it's it'll get more fantastic as it gets dark and I show you the slides. I think the important thing that Moysen said there, which has made my life very interesting in professional terms for the last 10 years, has been this engagement with glass as a material at a very one-to-one physical level. And I have to say, it didn't start out like that, and I think there's at least one person from Eva Jurikna's here tonight who may remember early conversations, probably in the mid-80s, when Eva was desperately trying to persuade us as engineers to believe in the idea that you could have a glass tread for a staircase. And we thought it was terribly impractical, being engineers. And there was even a couple of people in Eva's organisation, not the people who are here tonight or even who are with her now, but who also thought it wasn't practical. But Eva had a vision about creating this sculpture, this structure, and in a way was the inspiration and the moving force for us to actually address the matter and become interested in it. It had started in my own life much earlier when I was a student, when I read a great book which I still recommend to anyone who hasn't read it, which is called The New Science of Strong Materials, which is an interesting title because it's not as I used to think it was, the science of new materials. It's actually the new science of strong materials. So it's a new way of looking at something that already exists. And I think that's what's been fascinating about our journey with glass, is that it's actually been around for an awful long time, more or less as it is now. Soda lime glass, almost to the percentage, has the same constituents as when it was first made or known to be made about 2,500 years ago. So my slideshow, which normally takes an hour and a half, but I've now only got 15 minutes left, is going to attempt to describe our journey with this material and with the people, because it's, again, always about people, their inspirations, their desires, and their energy. And that's the people who, the architects, the designers, the sculptors that we've designed with, and the people who make glass, who are, I've learned, an unusual breed of people, and a pretty amazing group of people. I suppose they are in all industries, but as engineers, because most other materials are fairly well documented and codified, you don't actually get faced with a one-to-one question of what is it? What is this thing that we've got here? And there's a couple of friends of mine who are here tonight. I don't know if they got in or not, but they sent me a quotation for the millennium, which says, "People keep forgetting to go right down to the foundations. They don't anchor the question mark deep enough," which is a Wittgenstein quotation. And I think that's really what we found with glass, that you really can't anchor the question mark deep enough. There is so much to be known about something which is so common, probably in building terms one of the most common consistent materials that we use, but there's so much to discover, as I'll quickly show you. So, on with the show. This probably inspired Eva, who knows? But it's quite clearly a very early photograph, 1950s, and it's probably safety glass. This is actually not safe, right? So those girls are quite brave. They know a little, but they don't know enough. The reason I say that is that there's a phenomena called nickel sulfide failure. So although that's toughened glass, nickel sulfide failure has the peculiar quality of just happening just like that. So that toughened glass could go in a second, and I'd like everyone to remember that. And I'd like everyone to remember, because there's been a lot in the press recently about glass and about glass failures on roofs, etc., etc. And it's been said that most of those failures were following the guidelines of codes of practice which exist, and that I think is true. But what I would remind everyone to think about, and there are engineers and architects here who specify glass, I'd like everyone to remember what happens when the glass breaks, right? Always ask the question, because that in fact is a question that is applicable to every glass assembly I know, because glass can break in every situation, so you have to know what happens when it breaks, and also how you replace it when it's broken. And the very first thing that we did in glass that I remember was in 1987 with a practice called Paxson Locker, and they wanted to build a glass staircase and a glass floor, and we rang up Pilkingtons because that's the money, which is a reasonable idea. And secondly, maybe they don't know, or maybe they don't know in the way that we need to know it. So what they know to do what they're asked to do, but when you ask beyond that question, you're then into no man's land, or we were at this point. So this staircase is designed in accordance with Pilkington's recommendation. It's 25 millimeters thick glass, and it spans about 300 millimeters. And the reason it's safe is because it's so thick, it actually can't be broken right through, so your foot couldn't go right through it. And when it cracks, it's supported at least on two sides, and in the staircase treads situation, it's supported on four sides. So the crack would happen, but the glass would remain. So that's how that works. Now this is Eva Jurikna's staircase in Sloane Street, which is now gone and I believe rebuilt in somewhere in either Sweden or Denmark. And this is actually quite a different solution, and it wasn't engineered in the first place. I think it was suggested by a contractor in Los Angeles where she was doing this staircase, and she finally got a situation where she could use glass treads, and she put them in aluminium trays, and they kept on cracking. So the contractor said to her, well, why don't you put some acrylic between the aluminium tray and the glass, and that will soften off any hard edges. So she finally thought, well, why have the aluminium tray? Why don't we just use the acrylic? And in fact, it's quite a subtle result, because you couldn't use the acrylic on its own because it scratches very badly, and it's terribly flexible, so it would become very, very thick as a material. And the glass is ordinary annealed glass, so it's not toughened or laminated, it's just a sheet of ordinary annealed glass. And the whole way this works is that if the glass cracks, then the acrylic tread, which is underneath it, quite simply holds the glass till you come along and replace it. And I think this was there for about, this was 1990, so it's probably there about 8 years or so. And I heard of one cracked tread during that period, so it's quite interesting that it can work, be robust, and be very serviceable, and obviously very elegant. There's the detail close up. You can see the acrylic, and it's quite nice here because the glass has that beautiful green edge, and then you have the clear acrylic underneath. I think most of Eva's staircases use this method very successfully. This is one in a private house, and you can see if you're. Is there one of those little red pointers? You can see we had to build a little glass upstand on the back of the tread to comply with the staircase rule of no gap greater than 4 inches, for babies' heads getting stuck in the thing. But it can still be, as you see, very transparent, and you hardly even notice that. And that was the central tube, which this was actually cut out of a steel tube to give the to give the support to the inside of the treads, which were very, very simply just bolted down through a hole in the annealed glass. You can put holes in annealed glass, by the way. we had two letters, one from Pilkington's equivalent in America and one from Saint-Gobain to a client recently, thank you very much, saying, under no circumstances should we hold put a hole in annealed glass and put a bolt through it, which is patently untrue because these staircases have been there for a long time and they seem to work very successfully. So the glass industry will tell you a lot of things that you should and shouldn't do, but it's always worth asking the question a little deeper, because that's what we're consultants for, or engineers, I think. This is a third method of forming staircase treads, and this was the first project we did with Jamie, and it's a very simple use of glass, very effective use of glass, and the most I think the most elegant part of this is the central core, which was made by a wonderful guy called Tim Macfarlane and his company Tri-Pyramid in Boston. He actually knitted that basket together of I think it was 4 or 5 mil wire. I think Luke, who's here, who worked on it, could. Luke, 4 mil wire? 3 mil even, right. And they were welded together. They came in 2 halves and was welded together on site. It was quite an exercise. But well, I'm talking about principally glass tonight, and this is the makeup of the tread. You can see it's actually, we didn't even, I think Jamie just specified that. We didn't even look at this in truth. But you can see it's 3 pieces of laminated glass, laminated with a very fine laminating material with a sandblast on the top. And that's the support condition underneath. We had 2 little spars onto the basket. We really started asking questions about the strength of glass with this project, which is a Rick Mather project, now in Zen Reston. It's still there in St Martin's Lane, so if anyone wants to go and pass it, you can look at the pavement lights, which actually go across that gap there, which is about 4 meters, with these supports at about 1 meter centers. So they're big slabs of glass, and they're on a public highway, so they need to take a truck wheel sitting here, right? Because the truck's come off the road, crashed across the pavement, and it's sitting on your glass floor here. So that's quite a heavy load. And we designed this, and we tried to find out what stress you should take in glass, and we asked everybody, and nobody could give us a straight answer. They won't give you a straight answer. Do you want a straight answer? I'll give you one. The straight answer is that with annealed glass, which is the glass which just comes out of the float machine, the stress varies from about 130 newtons per millimeter squared down to about 20. Okay, that's why no one will give you a straight answer, because it's a fantastic variation. But with toughened glass, it almost universally, if it's toughened properly, has a strength of about 150 newtons per millimeter squared. Anyway, I found this book finally, which was a 1940 publication, which had the tensile stress of glass in it, okay, which was amazing, because I used that figure and I divided by 10 because I didn't trust it, and I didn't know anything else. Now the funny thing is that figure was 70 newtons per millimeter squared, that figure. Now I told you it went between 120 and 20, right? But in actual fact, what it represents is the average strength of glass for 3 seconds, with a load on it for 3 seconds. So you say, well, why 3 seconds? Well, that's what the British standard used to be for a gust of wind, right? A gust of wind would last 3 seconds, and then it comes off. So that's where the figure came from. But this is not wind. This is like people standing on here, right? For long periods of time, certainly more than 3 seconds. So my guess was sensible, because, in fact, the European Code of Practice, which has just come out, I think recommends 7, which is the same figure we use, which is an amazing kind of coincidence, but sometimes your intuition's valuable. Anyway, these are created by using 2 pieces of 19 millimeter glass laminated together, annealed glass, the idea being that if one cracks, which is what annealed glass tends to do, rather than shatter like toughened glass, if one cracks, the crack might go across there, and then it will still span between the other three sides. Okay, so you have a very safe system because that's just one sheet and you've got two. And I've designed one for this very low stress. That's it at night. You always show glass in the day and at night because it always looks, looks good at night, usually. This was our second kind of considered engineering problem, and it was a little conservatory for Rick Mather. And Rick always wanted his structures to be lean and really not to be there. So we finally, having done the pavement lights, which we also did with him, we stepped right out and said, why don't you just have glass beams instead of steel posts? There was a number of things which inspired that and a number of things which we saw, and in fact one of them was an article that about Jamie's work that I think Luke had some part in building design in just before this, and in it he talked about this beam, this glass beam. So it stuck in my mind, glass beam, I think. And when we proposed this solution to Rick, I thought, crikey, I don't know how to do a glass beam, I have no idea. So I rang up Luke and I said, Luke, do you know that article you did, you had that glass beam? He said, oh no, that was never built, he said. I thought, oh, I'm deep, that's the problem. Anyway, in desperation, I thought the thing through, and finally, the way it works is that these sheets of glass are actually, or these beams are made up of 3 sheets of glass. So it's laminated glass again, and it's using the glass so that if one piece fails, you might get a crack there, you still have the other 2. Even if 2 failed, you still have the other 1. And even if all 3 failed, the laminate would probably still hold it together. And even if it didn't, that roof panel would still span between 3 sides. So you've got a lot of, that was through hours and hours and hours of staying awake at night thinking, how does this, what if this happened, So you go right to the nth degree to think the problem through, which is where the fun starts. That's where the question gets deeper, and that's when you begin to know what it feels like, or what those 19th century engineers must have felt like, And the funny thing, that when Moyson was speaking just now, he talks about that, having the thing in your hand, really. And if you ever read The Tower and the Bridge, which is a book about engineers and their achievements, almost every single one to a T concentrated on one thing, and actually in most cases owned the firms that were making them. Apparently all of Nervi's structures were designed and won in competition on price. Right? Now, if you've ever looked at any of those structures, you think, wow, how could he have won that on price? But that was because he knew enough about the process, about the making, about the engineering, and about how it could be put together to actually both propose something new, something beautiful, and the cheapest thing, which is a great lesson. Anyway, this was my, I think, real sort of beginning of starting to look at glass, and we got this thing built. Again, it wouldn't have been done except that there was a glass guy, Furman's in the East End of London, who made this. And they were introduced to me by Pat Carter, who, both of those guys made this happen as much as anything, as much as Rick or I or anybody else. And a client who had the nerve to and the finance to pay for it, because it wasn't cheap, These glass panels they had a heat film on them in Finland. They were then transported to Germany to get the glass spacer piece in the middle there, and then transported back to England. And they broke the first time round. So you can imagine how much money it cost to get them there. But, when it was built, it was completely structural glass with silicone, obviously, sticking it together, with the radiators on the windows. Okay, because it's got heat film on it, so you don't need radiators. So Rick Mather was delighted because he had no visible structure and no visible services. You still had to pay the fee. At least the client did. So this was that little project, and that was the first. And there's the junction between the beam and the column, which is really like a mortise tenon in timber, like plywood. It's a wee bit like plywood, this use of glass, which if you think of it like that. Actually, what I'd love to do is, you know those Japanese joints? I'd love to have them made in glass. I think that would be, because then you'd see every bit of the joint. And you could do that with Peter Aldridge, could do that from Corning. He does that with glass. So, this is its big brother, which was done sometime later, a couple of years after that. But what was learned in the first one was that, you know, you shouldn't really go to Finland and get glass in Finland and then sent to Germany. You should really just live with what you can purchase. And in this case, and also if I go back, you'll see the beams in this one are actually curved. I know it follows a structural diagram, but it costs a fortune. All right? So you want to have them straight because that's cheaper. So this is the 2 or 3 times as big structure at half the price. So it's beginning to be understood now what you do and how you do it, and it's very similar in concept, but in this case we don't have glass spacer beads in the panels, and we do have a little bit of sunscreen on the top there. Various images. This sunscreen is quite good to have in the roof of structures because you don't see the bird droppings, you know. It's quite nice. Nice shadows. That's them putting it together. Again, this is Furman's team. I think that's John there. John Hodgson. The accuracy of doing this is, you can imagine, that's 30 mil wide, and they've got to sit the glass panels on top, so they actually built these aluminium spacer sticks so that the thing was exact. You know, they didn't have much room for play there. But once it's there, it's quite stiff. This is the beginning of another kind of investigation, and it was done fairly unconsciously at the time, I would say. It's from an engineering point of view, it's another Eva Jurikna staircase, and the treads are the same as before, but this time you'll see that we've actually supported the treads on the glass infill panels. And it really is our first kind of move into loaded, bolted glass. And it's again using a failsafe. We've got 2 sheets in there. And it's a funny failsafe because we've got 1 sheet of toughened and 1 sheet of annealed. So it's kind of muddled thinking. It's not brilliant thinking, but I haven't heard of it having broken yet, so that's quite good. It's funny actually, you know, with all the glasswork we've done, the only breakages I heard was that 1 tread on the Joseph staircase and a panel on the little conservatory, Keats Grove, that, you know, went. I don't know why it went. Probably might be nickel sulfide in the top, something. But the main structural parts, touch wood, we haven't heard a great deal about breakages in service. We've had some teething problems getting some things in place, but generally once they're there and serviced, they tend to perform reasonably well. This is another little staircase that was done with Brooke Stacey Randall for the Pet Shop Boys, or one of the Pet Shop Boys. And it's a glass staircase using rods top and bottom with the glass tread and riser. That's the riser and that's the tread, acting as the truss for the staircase as a trussed element. And we did some tests on this, and we went up to 5 times the design load on the staircase, and nothing happened. So we began to learn just how strong the whole material is. This is the project we did in Tokyo, which was probably the most challenging and exciting and educational that we'd ever done. And this is a little sketch as a response to a fax I got from a friend in Tokyo who said, could we design a 10-meter spanning cantilever canopy all in glass in Tokyo? Now the first thing you know as an engineer is that Tokyo shakes. And glass and shakes don't go well together in one's mind. You know, you sort of begin to think, ugh, that sounds nasty. But anyway, they offered me that if I got a solution I could go there, so that got me thinking. And I thought, well, maybe you could make it in bits like that and join them together. And so that was my first sort of response sketch, that I would use them like corbels to corbel out bit by bit. Because I knew you couldn't get a 10-metre long piece of glass to do the job that would work. You couldn't get toughened glass that did that. So I worked out the maximum shear in there, and then I thought, I haven't a clue whether it was 1.2 tons, that figure. Based on the idea of about 5 kilonewtons a metre squared on this thing, which I thought you might get from typhoons. Anyway, I didn't know whether I could get this or not, so I rang up. This is where we really get into the relationship with the maker. I rang up John Hodson and asked him if he could make me a couple of fittings like that to go on a piece of glass, and could he put it in a test rig for me. Right, there's the 2 bolts that went through those 2 holes. There you see the glass just sticking out the end there. It's actually 2 steel channels and the glass is in the middle. And then I slipped that little piece of wood down onto the top of the glass, and then we loaded it up like that. You see, with these big weights here. And that gives you, the reason we did that is it gives you a nice sort of cantilever, because that force times that distance equals that force times that distance. So you magnify the force, in effect. So if you've got, you know, a ton here, you get 6 tons here. And that's indeed what we got. And we discovered that the glass, that little fitting, could carry 6 tons and the glass didn't break. So I went to Japan. And before I went, 2 very good friends who supported, encouraged and drove me along during that week said I should pop round and pick something up before I went. So they gave me this little box, and when I got to Japan I opened it up and it had a little model. And there it is. And you know, if ever you want to, any students here, if ever you want to sell an idea, make a model. You know, and surprise them as well, because I didn't even tell them I had a solution. I just said I'm coming to Japan. I didn't tell them what I'd done or anything, but I knew it was a winner, and I knew it would work. Somehow I knew it would work. And I think the momentum of the surprise drove it forward, because we had 3 months of real torturous problem, trying to convince the Japanese, who'd been looking at the problem for 7-8 months, that we could do what they couldn't. They were really upset initially. And I remember, where's Kisa? I remember going to my first meeting, and I couldn't speak any Japanese, and the Japanese engineer from Asahi couldn't speak any English. And so we were all gathered there. There was tons of us there. And they'd seen the drawings, you know, and they were looking. And anyway, they produced this sketch. He produced a sketch. This goes over it's an entrance to an underground, so there are kind of steps going down there. And he produced this sketch with a man lying on the steps with one of these beams in his stomach. And he said, and he said, "I'm very worried." But he had a point. So we had to make sure that didn't happen. So we went through a lot of pain and torture. And the other thing about Japanese industry, and particularly Asahi, is they were amazingly efficient and clean. And they had things like, I mean, they had like white coats on in their factories, and they were all smiling. It was wonderful. I mean, they all did everything in unison. And of course, the odd thing was that they couldn't make these glass blades for this structure. Funnily enough, because they didn't have a machine to toughen the blade, and they didn't know how to toughen it. Our man John from the East End, he had a machine that could toughen this blade, and he knew how to toughen it. So But the worry was that Asahi were fronting this job, and Asahi had to take ultimate responsibility. And I didn't want them to meet John. Not that there's anything wrong with John. John is the best of the best, but he doesn't wear a white suit, and all his workers don't smile all the time, you know. And in fact, he works bloody hard, and he's got debris all around him because he's thinking about the thing in hand rather than what it looks like. And it's not very big as a place. It's getting bigger now in the last couple of years, and but at that point so we finally waited till this was made and like that, lying on the table just like that, till we finally took the Asahi guys down there. And of course, when they looked at it, they all got their tapes out. That was the first thing. They all got their tapes out, and they kept going, ha, ha, you know, because it was absolutely precise. Because my architect friends who'd taken me through the first part of this had gone down and sorted out that their machine, which they were cutting to plus or minus 2 because that's the industry standard, could cut to 0 tolerance. The glass guys didn't know that. They didn't need to know that. But they found that out. So they geared the machine up, and we cut this thing to like bang on accuracy, which we needed to do for this particular structure. So we took it, and they gave us a whack of money. They gave us £50,000 and said, go and do some testing. So we said, right, let's go do some testing. So this is it in the laboratory at City University in London. The first go around when they were cranking this thing up with a load on it, the bolt broke, much to the chagrin of the lab assistant, who in 72 years of his life had never seen such a thing. So he was like a born-again person. You know, he got all these textbooks. He said, wow, he thought this was a joke, breaking glass, you know. But the theoretical breaking load of this broke probably at about 9 or 10 tons, but the theoretical, if you can get that hole right in the middle, it's about 19 tons. It's quite good, isn't it? It's quite heavy. That's how it breaks. You can see it goes into lots of really small pieces because it's very highly stressed. That point. That's the boom. It's the failure there. It's wonderful when it goes. Everyone's nerves go, oh, bang. I can't stand it, to be quite honest. I mean, every time I go to glass testing, I can't stand it. Anyway, we went through these amazing hurdles to finally get it on site and built. And this is the jet. See what I mean? See how beautiful they're all exactly the same? And the other funny thing was that having gone through all this testing and proved we had factors of safety of 12, there was someone from the contractor who was actually an architect, Suzuki-san. Suzuki-san, all the way through, never said a word. He was the only one who never smiled, you know. And we took him to the best restaurants in England. He still never smiled. Until finally he said something, and it was after 3 months. We'd done all our testing, and he said, I want to see some acrylic. We said, what? He said, I would like to see some acrylic. We said, what do you mean? He said, like your staircases. We thought, oh. He said, for fail-safe. We thought, but it's got a factor of safety of 12, and there are, 25 blades, and if one breaks, the next one will carry it, and if that breaks, the next one... He said, nope, I want to see acrylic. So they made these things which cost more than all the glass put together, and they went in the job. There they are. They're in the core of the thing. They do absolutely nothing at all. Right? They've got enormous tolerance here because their temperature movement is, like that. And it would only be if the whole thing completely collapsed, that they might at the end actually stop it touching the ground because they deflect about 5 feet. So they're in there as like talisman, and the only way we could get it built was to do that. And that's how it ended up, as a complete glass structure. And we really had the time of our life. And we had the time of our life because we got hands-on at every level. And that was the real joy. And hands-on, being an engineer and not knowing where you're going, that was a real joy. Because every day is a discovery. Sometimes a shock. But inevitably, you see these acrylic things? Up there? They're all right, actually. I think they look fine proportionally. maybe it was an architectural sense. Maybe he architecturally didn't like it, and he wanted them a bit fatter. That was an excuse. Funny reflections. And there's a little detail at the top that holds the roof panels on, just a little metal fitting in the middle. You see, you transfer the load from one to the other, so you get lots of purchase across that distance there. It keeps the load in the bolt down. That's why it looks like that. Anyway, I better hurry up. This is the glass cube in Saudi Arabia that we just finished. Interesting thing about this is friction grip fins, which are laminated, not single sheets, which is normal, and in two directions, so that we can, so the thing works as a two-way structure everywhere, and it's got lots of fail-safe in it. The other interesting thing is these panels of glass on the wall are single sheets of 15 mil, and they just sit one on top of the other, right? And they're just silicone back. We believe in silicone. I know some people don't, but nobody's proved to me that it doesn't work, and I've had some proof that it does work for a long time that I like. I mean glass to glass. People have proved to me it doesn't work on stone, and that's true. And this is our engineer out there, hands-on, trying to work out why, when they were tightening these up, they were getting breakages, which they were. And we discovered that they were putting them together wrongly. This was the Saudi company that were actually making these. So he went out, got his team together, there they are, and then they built the cube. It's nice, it's a local firm, and they built the cube, That's the other thing, in the industry, the glass industry. Often the big boys say, well, we're the only guys who can do it. But, if you get hands-on and you really get down to it, you can do a lot. And that's it, put together. You can see the two-way plates there, and we've even got little diagonal plates in the corners there. And it's even got doors in it, which is kind of nice. And we told our engineer not to come back till he'd walked on the roof. He did come back. He's back. That's him. Anyway, the idea is that they're laminated. If one breaks, you still have another one. Even if the whole beam went, the laminate material would keep it there because of the bolts on the laminate material, and the beam would span the other way. So it's all good. So that was from the small. This was supposed to be also the small to the conspicuous, in the sense that starting from a small idea, where does it eventually go? And we got through the Tokyo Canopy experience a chance to do this facade here, this bottom part here, which basically has horizontal beams spanning 11 meters between the column positions, which are there, and carrying the insulated glass panels in between. And these horizontal beams are actually external. There you can see a kind of, that's during construction. And again, this was built by a local glass company. Piltz and Asahi said it couldn't be done. And the glass company director took me out one night for lots and lots and lots and lots of drinks, as they do in Korea, at the end of which he said, if this doesn't work, and then he didn't finish the sentence, but I could imagine. Is it time to... it's time to hurry up. Yeah, right. Okay, so that's a shot of it. That's another shot of it. Okay. That's it. And these are castings which it was great fun, because they couldn't make them either. And our friend Tim Eliasson came out to help them. And these rods here, they actually have a belled end on them, which you make by putting in a big press and pulling, and it makes a bell on the end. So he told them that's what they needed to do, and they said, we're ready, come out and inspect. And they had one of those JCB diggers with a hammer on the front bashing a rod. Honestly, that's what they were doing. And it looked like an old turnip, He couldn't believe it. He phoned me up and he said, I can't go on with this. He said, I've got to resign. I said, Tim, stick with it, please. Anyway, he did, and they finally built the right machine, and they did it. And they made a nice job. And that's us testing it. And I remember Sean Billings, who's also here tonight, because he worked in this too, saying to us, we were doing the test, and he said, why are you doing the test? We said, well, we need to see if the water gets in. He said, are you using silicone? I said, yeah. He said, it's a waste of money. The water will never get in. Even if it does, you just put a bit more there. He's quite right. That's how it is. That's what silicone's like. That's why I kind of like it. Anyway, this eventually took us, these are sort of 3 jump steps, and there's a lot in between that I can't really show, but I'm taking you to the small to the conspicuous. This, if anything's conspicuous, I think this probably is. It's the building that Vignoli invited us to work on him with as engineers for all of the building, not just the glass, but the whole building, and particularly the roof, which is quite interesting. It's a folded plate barrel vault Vierendeel. How about that? There's the folds which give it its stiffness. Well, it's a barrel, obviously, because it's a big barrel. But just to go back a shot, the interesting aspect is also that it's a Vierendeel beam, and a Vierendeel beam just means that these elements, instead of being diagonals like you normally get in trusses, are vertical and are therefore in line with the glass, which can be normally cut as rectangular panels and put together, and it's fairly big. That's a big 2,500 seat concert hall. And we're also doing the end wall in this in something that, when I was round Jamie's office one time, he showed me this model of something they were doing in Germany, and I said, "What's that?" And he said, "It's something we're doing with Jörg Sleik." And it was a cable, which he undoubtedly will show you. Anyway, we kind of thought that was amazing to do such a thing. So we've actually done something using those principles on the end wall here, where we've got cables at about 4-foot centres, but instead of having horizontal cables, what we're doing is that we're weighting these cables in one direction only, and we've got cast iron weights on the bottom of the cables. We've got a whole row of cast iron weights along the bottom there, and when the wind blows, the wall moves quite a lot, but that's about 180 feet, which is about 60 metres or something across there. So the big weights are just in there, and they're just in one direction. Our mock-up is in about a week's time, and we're going to get down and see what happens. But again, it's moving the Americans. The Americans don't normally do this kind of thing at this level contractually. They all get a bit worried about it. But we've got a local glass company doing this, National Glass. They're rather amazed at doing it, but they are. And anyway, that's my story so far. If Moisen asks me back in a couple of years, we'll tell you what happened. Thank you very much.
Great, thank you. That's always inspired by Tim's work. We find his enthusiasm and energy and inspirational in our office and work together often. I was hoping to speak this evening a little bit about some of the projects next door, but only briefly about one or two of them in a little more detail than is possible to show in the exhibition. But I thought it might be more important to speak a little bit more about what we're both trying to communicate in that show, which is really the sort of the fundamental beginning of a design project and the making of the project and the final installation of the project, which I think in our studio, which is a fairly small studio, myself and Luke Lowings, who's here, and Richard Kress, we're a small studio, and we collaborate very, very closely with fabricators and engineers, with Tim and Tony Broomhead, who is here, and others. And I think it's an unusual circumstance that we are so closely aligned with all of our team members, really from the very, very beginning of a project. And when Moisen first began the introduction speaking about someone like Prouvé, I mean, Prouvé, we have to remember, actually studied as a blacksmith and understood his material, metal, in all of its forms, both from its malleability as a molten material, right through its cold forming states in terms of break forming and drilling and other means of manipulating the material. And I think that that's something that we often lose in terms of understanding how complex materials are, not just metal or wood or specifically glass in our instance, but we tend to categorize a material within one state and somewhat ignore its capability of transforming itself through other states, both liquid and solid states. And it's in those moments of transformation that a material, I think, begins to sort of express itself and allow itself to be understood. And some of Tim's comments about how materials are so clearly defined and categorized in terms of engineering textbooks, in terms of what their physical characteristics might be in terms of building construction, often looks at a very, very limited avenue of the life of that particular material. And I think that what we respond to when we see people like Prouvé and people like Nervi, we're seeing people who are actually delving into their material as craftsmen, but I'm not speaking of craftsmen as artisans, but really craftsmen who, one might use the word craft as someone who understands all the permutations of the material within which they are disciplining themselves. And for ourselves, we're operating in a very limited field, I mean, in terms of our own work in glass, and we try to enlist all of this input and help. And my own background, of course, is probably more closely related to the actual working with glass, as I worked in the glass directly and worked with Corning before starting a studio about 20 years ago. But there's that component that I think we have to understand about materials, that there's this incredible breadth of understanding that needs to be had about the material before you can begin to really work with it. And then coupled with that, I mean, I don't want to just exclusively sort of focus on sort of the structural elements or aspects of the material, but there's also, for our work, working with something like glass, there's also a phenomenological level. And all I really wanted to speak about today was really briefly go through a few projects and try to make clear this sort of coupling of structural exploration simultaneously with an aesthetic exploration, which really deals with, I'd say, the much more ephemeral characteristics of a material. And I thought that I might just start with this. It's a very early project. It's from the mid-'80s, really based on some work even earlier than that, but it serves as a for me, in some respects, a very simple project, never built, but a project that really does try to couple these two things of both structure and sort of the ephemeral nature of a material, in the sense that a material can bring about a much richer way of expressing a site or a context. And in this instance, it's a very simple idea. This is a bridge, a glass bridge, designed in such a way that in order to cross the river, the glass platform, which is all post-tensioned, highly compressed glass planks, is basically supported off of these two cantilevered abutments. So you have an all-glass platform floating over the surface of the river, and the notion here is that you really, in terms of crossing the river, that your movement or your participation in the landscape is really moving onto this glass platform along the river itself, moving in the direction of the current of the river, against the direction of the river, and then over to the other side. So the notion of just crossing the river engages you with the movement of the water, and the use of this transparent material similarly has a direct connection to this passage over water. A very simple diagram. This is what's called a Lauricolet truss, a queen post truss, by an engineer that we all admire. And the glass planking was designed in such a way that, I'm not sure I can focus here, but the goal here was to not only use this glass platform as this very extraordinary glass form floating in space above the river, but to take sunlight and use the activation of light to let the light come down, strike the surface of the river, and then reflect back up. So this glass platform basically is the surface of the river, sort of extracted upwards, and it becomes the surface upon which you pass over the river itself. And I think that just very simple notions of that, engaging our movement through a space, both in urban context, or in this case more, very much sort of a rural context, but using these structures as a way to sort of open up your sense of how you relate to your surroundings is a very, very critical element of all the work that we do in the studio. And by taking one of these very simple principles, this is the principle of the same as on the bridge deck of post-tensioning glass, and this is a project done with Tony Broomhead, who's here. This is basically a wall. It's a glass wall done for a project by Richard Meyer, and this wall basically separates a private art collection from a private residence in a private residence. And it's designed with a counterweighted system so that the glass wall basically descends down into the basement of the building, and then when they want to separate these two spaces, the wall is deployed and comes up into the space. And it was a study really of two things. One being, how does one basically take a stack of glass, and I'm talking literally of a stack of glass, basically stacking glass plates edge to edge, two stacks with a stainless steel rod running down the middle, and putting enough compressive load on those glass plates that that's all the structure you need. You're putting so much tension into the system that the glass basically has no other restraint except for the compressive load. And simultaneously, by taking these two surfaces, playing with sort of the phenomenology of both surfaces, the one wall facing sort of the collection area has a very highly reflective surface to it. It's still transparent, but it's a heightened level of reflectivity, slightly higher than a clear piece of glass. And then the reverse surface is totally diffuse. And to do projects like this, and this is, I think, where Tim's speaking in advance of my own speaking is very appropriate, because I think we follow very similar avenues here from the point of view of wanting to work with a material that none of us really understand in all of its potential strengths and weaknesses, and therefore all of these projects demand empirical testing before you can move forward with them. And in this case, you're seeing the two stacks of glass, one series at the front, one series at the back, stainless steel rod running through the middle, and putting a significant load into these pieces of glass and then trying to break them. In this case, you're basically seeing the glass, trying to break it. We couldn't break it utilizing any of the normal testing procedures, which is swinging 300-pound weights into the glass itself. And then we needed to essentially just break the glass, which we did with a hammer, sledgehammer, to find out what would happen, because you would imagine by stacking these glass pieces edge to edge, putting such a serious load on them, if you were to lose one panel, that the whole system would be a progressive failure. The whole thing would come down. But what we learned on this, both the panels being laminated, is that the glass, in fact, because it's under such a high compressive load, the fragments actually can't go anywhere. They're basically all held into position just through the loading of the system itself. And here you see the wall sort of in partial deployment as it comes up out of the basement, very quietly, very, very beautiful, just sort of slides up out of the basement and separates these spaces. And all you have at the floor level is this stainless steel bar flush with the ground when it's down, and then this thing comes up out of the floor to separate it. And you can sort of see in this instance sort of this heightened reflectivity on one surface, and a detail of how those rods run down through the middle. So it's this exploration of, as I said at the very beginning, in this case, focusing on a very, very specific task of compressive loading of glass. How can this be developed? How can this then lead to larger projects? And using these small-scale projects as explorations in that sense, but simultaneously overlaying them with this goal of playing with reflectivity. And then taking this to another level, I mean, using glass as a compressive material, and this again was with Tony, who's here, is this project, which is in Hong Kong, and this is one of the projects next door here in the gallery. And what we tried to do in the gallery exhibition was not necessarily just show drawings, but try to have you participate in some of the installation sequences by using those photographs and slides. And we actually do the installation work. We actually oversee fabrication, and we do the installation work. And I think it's critical to understanding what happens with these structures when they're being built, to then be able to take them to the next level afterwards, to be there and to sort of really understand what's going on with them. But what you're seeing here is this pair of helical nets woven that create the tensile net that will ultimately hold all the glass pieces in position, sort of the scaffolding that goes up around this piece. The nets are hung from this ring. There's one helical series of nets in one direction, then an opposing helical net in the opposite direction. They're all woven together and then preloaded at the bottom. Very, very significant amount of weight added to the bottom through water. Basically stretches those cable nets. Then all the glass is put into the woven cable nets. And here it is all coming up, the last pieces of glass going in. These are the cables. These are also, they're about 3 millimeter diameter cables. The last pieces of glass go in, and as you're progressively building the piece, you're slightly removing preload, so the whole piece goes into compression once all that preload is removed. And a comment that Tim had made, I think, is very critical to doing structures like this, and that's the ability of the machinery today in the glass industry to actually manufacture parts with essentially zero tolerance. I mean, you can actually build pieces. In this case, this is about a 25-meter high structure. Tony had completely calculated out all of the different conditions of this piece under its preloading, and then it's loading with the glass. And you're able to build something like this over that length to 1 millimeter in dimensional tolerance. And part of that's due to the fact that the glass is being cut with these water jets and other equipment that allows for that to take place. So anyway, here it is. It's sort of this, just working with a shell. It's basically a glass shell structure. And the obvious next step is you can build in a complete structure. It doesn't have to be a piece of sculpture. It can actually become a room, a building, whatever it might be. But you can actually use the glass bearing on its adjacent panel of glass in compression to actually build much, much larger structures. Other projects, I mean, the project that is shown next door is this one, which is in the Phoenix courthouse, and is done with Richard Meyer again. And it's an interesting project in the courtroom. This is a very, very large public atrium space. This is an immense volume here in Phoenix, Arizona. Obviously, very, very, very extreme climate. It's all naturally ventilated, using misting systems to provide cooling in the summer, and then just natural ventilation in winter. And in this drum, which is this courtroom, which will be used for major cases and naturalization processing, we were asked to then design the ceiling or roof for that courtroom, and here's the building under construction. That drum is inside, and the drum measures a little over 100 feet in diameter, and again, it's a cable structure, and this is shown in the other room, and this is a working model of this drum. And what we've tried to do here is there's two different components to the glass, which the outer circumference, sort of this flat roof circumferential area on the side, is totally clear glass. So standing in this floor area of this courtroom, you can look up through this outer circumferential area and look up to the sky above. And then the inner section here is actually a concaved spherical section. And it's made out of a diffuse glass. So it's essentially a fragment of a sphere floating in this clear ring, almost as if it's a bubble floating on the surface of the water. And that lens, that really is truly used as a lens. All of the lighting for the courtroom is at the very top of the drum, which is significantly higher than this model. And the lighting is directed down to this lens. That glass refracts the light, and then the light is reprojected down to the different judges' chambers and the jury benches and all of that below it. But what is interesting about this structurally, I think, is not only its cable net system, and this is a model that is used to anticipate the loading of this type of a structure. When you build the cable net, and then begin adding weight to it, the weight being the glass, the whole distortion and the ability to sort of predict how the thing will behave during installation is critical. So this model was really designed to try to get an understanding of how it would behave when you begin to load it. But what was of interest in this, in terms of the structure, is that we've actually taken the fire life safety system, which is the sprinkler system for the space, and we're actually producing or manufacturing the stainless steel sprinkler systems, and they're being put into tension. The whole fire safety system is put into tension and is used as part of the structure of the whole ceiling of the building itself. And it's only in these cases where if you were to take on a project and build it, you could really do something like that. And this is actual testing of the glass. This is Luke, who's been in charge of this project, designing it, testing the glass, coming up with ways to do it. This is the drum as it's constructed. And I would point out to you that you might look closely, those of you who are really quite interested in the glass technologies and how things are changing, but the detail that's used for attaching the glass for this roof is shown in the other room. And we're basically not attaching to the glass at all. We're using a very, very thick ionoplast interlayer material, very thick interlayer material that extends beyond the piece of glass itself, and it's actually the interlayer that's mechanically fastened to the structure, and not the glass itself. The glass is just resting in there. And these are views of that lens, computer views. This is just starting construction in the next about 3 weeks. These are the sprinkler systems around it, and that disc, the clear perimeter section, and then the central lens piece beyond it, and sort of what you would see from the interior. But I wanted to just talk about the use of light. I mean, I haven't really spoken about that in any serious way yet, but obviously I think something that intrigues us in the studio is the fact that glass hasn't really been explored very much, is, I think, really due to the fact that its presence is often denied. I mean, typically we deny the presence of glass as a material in a building. I mean, it's thought of in a very abstract way as a boundary condition between interior and exterior, but it's never really represented as something in and of itself, and only in few instances, you know, in some of Mies's work, where the simplicity of the structure and the surface reflectivity of the clear material is integrated into the concept, is it really explored in a much more, I think, complex way. And something that I think Tim is working with, and something that we certainly work with, is when you basically release the glass from a framing system. I mean, we often think of glass as having to be confined in some sort of a frame or subframe, but immediately when the materials sort of taken out of that frame, you're made aware of how light interacts or projects through it, and its own transparency, much like, you know, water or air, and light's interaction with it becomes much more apparent, and you're able to explore its properties to a much more heightened level. And in some of these projects where we're focusing just on light, and some of these latter projects I'm going to show you really deal mostly with light and structure, but I'm going to speak mostly about light, is a project like this, which is done, just recently finished before Christmas in Berlin for the German Foreign Ministry office, and it's a roof, a roofing system, and a curtain wall done with the engineers Schleich-Bergermann from Stuttgart. And it is a cable system, as Tim had mentioned. It's a two-way cable net, vertical cables and horizontal cables, highly tensioned, that support the curtain wall, and very simple cable trusses, lenticular cable trusses for the roof itself. But the whole principle of the wall is that this wall faces north. That direction is north. The sunlight, very much like London, obviously very high latitude, very low levels of light coming through the roof. The wall is basically designed to get maximum transparency at the roof level, use the structure and the roof supporting the beams to take that light, bounce light back into the space itself, and then in addition to that, to use this transparent front surface wall as a reflector. Very similar to the screen done for the Richard Meyer project. It has a transparent coating on it, about a 30% transparent reflectivity to it. So light that passes through the roof hits that surface and also bounces back into the building itself, as well as passing through it out into the street. So this wall, looking at an early model, showing exactly what I was just describing, light coming off the trusses, light hitting the front wall and bouncing back in, a way of sort of animating the space, very early study models of an earlier configuration. This was sort of an open, basically sort of a layered, lapped type of glass construction, how the light and glass would behave under different lighting conditions, daytime and nighttime, and then some computer renderings that were studied very early on, where, as I said, sort of the cable system at the header truss up above here and into the entry door frame below, very highly tensioned series field of vertical cables, which carry the dead load of the whole curtain wall, and then opposing that is a field of horizontal cables, which are basically cantilevered off of the front face cable, and you'll see the component for this in the front room. And cantilevering off of that back cable is a bar, basically a bar, a continuous bar of glass that runs. And what we've tried to do here is over the entry is a zone, basically, that is heightened reflectivity. This surface here is very highly reflective, surrounded by a frame of totally transparent water clear glass. So you have this sort of floating reflector in the center of the space, which you can see here. This is the actual constructed wall, where you can see the vertical cables at the front, this cantilever arm that carries the horizontal cable, these bars of a lightly coated glass at the front. But here you see the transparent glass around the frame, around the outside, and then this heightened reflective glass in the center. And what happens here is this playing with the interaction of reflectivities, where you're getting this bar that's intentionally floated to the interior, reflecting itself in this glass surface and appearing as if it's projecting out beyond the surface into the street, where you begin to get a much greater complexity to the depth of the wall. And I think that this is something we continually try to work with, is this idea of taking the wall surface and moving it from being simply a single plane of glass, but actually allow for this interstitial zone or boundary condition to take on greater dimension, and then within that dimension you allow these optical phenomenon to take place. And here you can sort of see that under, these are just shots that we took just right after construction, so we don't have final photographs of it, but it is finished, just showing it. And these are obviously like the lightest constructions you can possibly do with glass. I mean, there is no mullion, there is no lateral stabilization to the wall, and that means, as Tim was sort of mentioning in his, that means these walls move, and you've basically made a huge leap. And this is, I guess, should just be clarified that in the same way that Tim was mentioning Nervi's approach to work, and ultimately winning a lot of his contracts through least cost approaches to engineering. I mean, these walls, since they have no steel in them at all, you've made two jumps. You've made one jump in the sense that you've accepted movement. You no longer try to restrain the wall to resist wind loading. You basically allow it to move and behave as more of a net system. And then secondly, you've made that jump to not getting into drilled glass and not getting into a lot of the hardware and fittings that we've all become so familiar with in cable net systems that, or cable structures anyway, not cable nets, cable structures that have a very overt sense of structure to simply hold a clear piece of glass. And I think what's going on here is something very different. You're really trying to have the glass speak a much more complex language and a much more complex vocabulary, and the structure recedes and becomes less emphatic. And thereby, I think, enriching sort of your exploration and your experience of what's really transpiring at that moment in time, you know, within the lighting conditions of the space. So anyway, here's a very simple, I mean, I think this idea of sort of participating in construction, I mean, here you have the clear roof overhead and the daylighting reflectors inside. And so what we're really trying to do in all of our work is sort of integrate this role of the sort of aesthetic goal, a very heightened aesthetic goal, with sort of a structural goal. And here's the wall. There's basically, or there is no wall at night. There's simply nothing there. And I mean, that's one of the goals, that it's gone. And I just wanted to end on three quick projects, which I think are really geared more towards this exploration of light and how we would tend to approach working in urban spaces or in urban climates or urban environments, and using light and people's experience as a way of sort of unlocking various elements of the context. And this is a project in Berlin, unfortunately not to be built, but a project with Helmut Jahn where we were proposing basically completing this building with this translucent glass pyramid or triangular volume, prismatic volume that ran literally from the sidewalk up to about 14 stories, all done in translucent glass that could be lit at night. And then within that, another volume, a second volume that's basically set back from the outer skin, which creates a blue room. I mean, this floating blue room made out of blue glass that the public would be allowed to go up into this room. Has a very large aperture from which you can look out over the city of Berlin. The typical height of the buildings in the Berlin is this height here. So this element would have extended up above all of the surrounding buildings and sort of been this element on the skyline. And in this volume, both as a marker from an urban level, but also as this space that you would go up into to look out over the Tiergarten and other aspects of Berlin, you would have this experience of being in this very, very confined volume that basically opens itself up to the sky. So if you're in that space looking up, basically just this aperture to the sky where the rain would come in, but you'd be in this blue volume. And this use of materials, I mean, and this is an unusual project which is in New York that is purely about light. This is not a curtain wall. It's basically a rain screen on a building, and it's only about trying to register to you as the public or to someone moving through this space. It's right near Lincoln Center. How different the environment is from moment to moment, day to day, week to week. And what this is basically a surface at the background of two different glasses laminated together, a diffuse glass and a reflective glass. The light passes through the diffuse surface, strikes this reflective background, and then the light tries to come back out through the diffuse surface. But by nature of being a diffuse skin, you basically end up with what would be secondary and tertiary interior reflections. So the glass really luminesces in and of itself. And then perpendicular to that surface are these glass fins. These fins extend off the building about 2.5 feet. And they're very, something that's very intriguing about a project like this is that it's so simple. It's basically, if you were to see a drawing of this, it's basically just a grid with a few lines on it. There's nothing really here, and it depends entirely on your movement past it to really activate it. Like you would see this from one angle. I mean, what we just saw, somebody would see this from one angle, but at the exact same moment, someone else would see this from the other angle. So it's something that brings a totally different appearance depending upon what angle you look at it from. And as you move by it, it becomes a very dynamic element that shifts at all different times. So you're really participating in this change that takes place in the immediate environment. And you can get very extraordinary effects like this from it. And then just one last project to really sort of close on this idea of working with light and sort of seeing things in your environment or around you, and how you react to those things and how you extract elements from your experience and build something with it. This is a project that Richard Kress in the studio has been working on. And this is New York, and we have foggy days like you do. And we get these, we have these wonderful buildings that are lit very intensely at night. And when we get these low elevations of cloud, these buildings basically take over a huge area of the city. They're no longer single markers, but they all of a sudden influence a huge area around them when the whole sky begins to glow with these volumes of light above you. And sort of taking that principle was an invitation that we had to develop the gateways or the thresholds to the Olympic Park in Sydney this year. And this is something we've been working on the last couple of years, and this is now under construction. And the Olympics is really about reclamation of land, reclamation of toxic sites, sort of post-industrial landscape, reclaiming water systems, water purification. And we wanted to come up with an idea that would basically display a partial cycle of water recirculation, but do something with it which would be an extraordinary event as you entered the space or you experienced it. And taking this phenomenon and then working with these misting systems. These are commercial misting systems that are used for agricultural use, I think all over the world really, for controlling temperature when it gets below freezing. Using these misting mass as part of very large mass next to a roadway. The roadway that enters the Olympic Park crosses a very small mangrove stream, and coming out of that stream is a series of 10 masts, or 6 masts that come out of the stream. And the top of each mast has a field of these misting devices, so that up above you in the air, 25 meters in the air, is this actually artificial or synthetic field of mist being created overhead. And by using these, what we were exploring is how, if you're creating this mist in the air in the daytime, how can you create something with sunlight that would be effectively sort of an apparition or a mirage. And this is sort of demonstrating what the principle is, where you float the mist in the air, and by using a device called a heliostat, which tracks the sun all day long, and controlling the wavelengths of light that come off the heliostat through a filter, a glass filter, we're basically bouncing a beam of concentrated yellow light back into this mist, and you can get objects and forms floating in space in the middle of the day. And the goal here is that as you drive across this bridge, floating overhead will be this bar of light that essentially floats in the sky. And it's a phenomenon. We've already built the prototypes for it, and it's under construction now. But this is the roadway that the little model that's in the other room sort of represents this area, where you drive across this roadway, and this is the mangrove swamp, and the masts run across this. So it's basically bisecting your passage, and you move through this field of light and mist as you enter into the Olympic Park. And this is just demonstrating how it actually works. I mean, in the daytime. And what was interesting, that it's all this dealing with sort of atmospheric phenomenon. You would expect that the sunlight itself would dominate and basically wash all of this out. But by limiting the wavelengths of light here and having a differential in terms of the eye being able to pick that out, you actually get these fields of light floating in space. And these are some of the tests for working on it. And one of the early prototyping mass done down in Australia. But that's the last slide. But I guess I just want to reiterate this idea of combining an exploration of material and structure with this other component that materials have. And that component is this extraordinary phenomenological capability that they do have. So Tim and I think are supposed to talk a little bit, but we've probably both gone on longer than we're supposed to, but I'm sure I'd be happy to answer something.
Hi, Jamie. That was great.
You can do a little closing here?
Closing? No, we got to talk.
Discussion? Okay.
I don't know. Moisen suggested that we have you all ready to go home, or?
Or questions, or what?
Yeah, I mean, we could have some questions, would be one way to start it. Because we talk to each other quite a lot, so we've nothing else to say to each other. That might not be true, but does anyone have a question about it?
No? Okay. Well, I hope, thank you, that was good. Good to hear your talk. I always like to see Tim's slides.
Good to hear you as well, Jen.
And hopefully you'll enjoy the show next door over the next month, right? You think there will be? Everybody's so shy. Usually when you're in Germany and you ask for questions, nobody asks a question.
There must be some questions. I mean, even I was down at the University of Virginia the other day, and they asked some questions. There must be something you don't know. Yeah.
Just something really mundane about silicon glue. What is it that makes you trust it?
Well, I think it's because nothing's happened so far that's made me not trust it. So I've been using it for about 10 years, but the first time I used it was, I suppose, on that little project in Keats Grove with the glass beams, and the client was in the audience the night that I ever first talked about it, which was about a year after it was up. And someone in the audience asked the question. They said, the only thing that's making that stand up is the silicone, isn't it? And I said, yes. And they said, well, how long is it going to last? And I sort of looked at the client, and I didn't know how to answer that question. So the client sort of grabbed me afterwards and said, how is my building going to stand up? But the truth is that silicon has been around since, 60s were the first applications by General Electric, for example, in New York. And I spoke to the guy from General Electric's a couple of years back. And he told me they took a piece from that early first building they ever did, and he tested the characteristics of the material. And I will emphasize it was a glass-to-glass situation. And he said that they were exactly the characteristics as the day that it was put there. So, that's reassuring.
Yeah, and I think also, a lot of people, silicon's very different than other glues or adhesives, because silicone, of course, is the same as the silica in the glass itself. And what you have happen when you use silicone adhesive on glass is you actually have an ionic bond between the two materials. You're actually getting the silicone adhesive penetrating through the surface of the glass into the glass molecule, the silica molecule in the glass itself. And it's a very, very different thing. And if you ever clean the silicone off of a piece of glass, you're never actually cleaning it off. There's actually will always be embedded portions of the molecules in the surface. So it's much more than, it's not just a surface adhesive characteristics, it's really a bond into the material. That's quite unusual for adhesives.
I'd like to ask, as you talked a lot about structure. You know that James knows an awful lot about the ways of coating glass and the ways of techniques of achieving these surfaces. And it seems to me, could you tell us a little bit about what might the future hold for achieving new types of coatings, and how you understood this? Because this is another level which in a way I think you could expand and talk a little bit, because you have a lot of knowledge in the area.
Yeah, I think. The question from Richard Horton. The question was about coatings. Really, coatings is an area that is obviously changing the glass industry in terms of its of the ability of glass to basically perform at a much higher level in terms of its thermal performance. Actually, there was a fellow here a little earlier, Lauren Butt, who I'm not sure if he's still here, but one of the people who really worked very early on low-E coatings. But coatings technology, as the glass industry is so restricted between 4 or 5 big manufacturers in the world, the only real difference in the base material can be achieved through coatings. And the coatings emphasis can be either on this more commercial level that we're familiar with low-E coatings and things of that nature, or it can be on a very, very highly sophisticated level in terms of sighting systems and optical devices. And there are coatings that are, as we all know, in a laboratory level, are capable of doing most anything we would hope to have a glass do, meaning from photoresponsive coatings, meaning they lighten and darken, to electrochromic coatings, which are now on the market. But there's a huge future, I mean, for coatings and glass basically being both a passive and active participant as a substrate for coatings. I mean, that's obviously glass's role is as a substrate. And as the coatings, I think in terms of cost, become more, the demand is there. I mean, I think currently we're sort of seeing a demand for higher efficiencies in terms of these low E coatings, so that you can use larger amounts of glass in buildings. But as the demand grows, I mean, all of those technologies are sort of there, but there's been no reason to really bring them forward. There's not been a market to really bring them forward. But coatings is the future. It's a very complex field, and it's in many different avenues. But it's hard to sort of summarize it because it's so complex as a field.
Another question. What do you know about bending glass technology? Because all the elements I saw so far, they were plain. I know about interior design, in North Italy, they know how to bend glass.
His question was, what do we know about glass bending? And that they do it in Italy. Is that right? Actually,
Bending is, I mean, that's also a field which can be fairly simple, maybe very simple two-dimensional bends, or it can be very complex if you get into three-dimensional curvature, anaclastic forms. And, cars, basically, the automotive industry is driving both the coatings field as well as the bending field today. If you look at any sort of modern or current, cars, you see very complex glass forms on the car, which are actually structural to the frame of the car. A lot of cars today cannot pass their safety codes in the countries where they need to pass it without the glass being in the place. The glass is actually a contributor to the strength of the body of the glass, or the car. And coatings is similarly, I mean, the automotive industry, I think, is the one area where we see coatings being pushed. And that's just because it's such a huge market, I mean, to have sophisticated coatings. But bending, complex bending, I mean, three-dimensional bending is a very difficult enterprise, demanding, very complex molds, each mold individually made for each piece of glass. And that's what makes it difficult with bending. There's not a very simple repetition process unless you're doing a million cars, and then you can make the molds to do that. But individual bent shapes is very expensive. Not impossible, but very expensive.
Yeah, you saw, Jamie was just telling me about a Frank Gehry piece which he saw in New York, which looks like a Frank Gehry piece in glass.
Yeah, every single piece, I think 75 pieces of glass, every single piece was different. And these are very big pieces of glass, or the height of this room. And every piece is obviously very expensive. Maybe 20,000 pounds, 25,000 pounds per piece of glass. So it's sort of, the question is, I mean, is it really worth to have a piece of bent glass or not? Yes, at that level. But